Okay, so we have just for the slave, we have just to wait for the flag to be 1. Once the flag is 1, so as long as the flag is 0, we have to be looping here. Okay, if the flag is set, we have a skip. We have to read the data from the SSP buffer and send it to port B. Well, move FF SSP buffer, comma, port B, and you have to return back to check the flag again. So you can see it is very simple. It is similar to the TX transmission and the RC receiving. So in the USART, we have just 2 registers, one for sending and one for receiving. In order to send data, you have to put your data into the TX register. If you want to receive data, you have to read it from the RC register. In the I2C protocol, we have just one register, which is the SSP buffer. We can use this register to send data and to receive data. So as I said, in SPI, we are sending and receiving at the same time. If you send data, once the data transmitted, at the end of the transmission, you will receive the data from the slave. Is it clear?
Yes.
Okay, so here we didn't use interrupt, use just the pulling technique. We are just pulling the flag. We're just testing this flag. We can do it with interrupts. Okay. So with interrupt for the master, if the flag is 1, so for the interrupt, you have to use the IF. So for the SPI, we need the SSP IF, which is the SSP interrupt flag, which is the bit number 3 of PIR1 register. And to enable the SSP communication, so we have the SSP interrupt enable. So this is the interrupt of the SSP module, which is the bit number 3 of the PIE1. And for the priority, it is the bit number 3 of interrupt priority register 1. So if you want to use interrupt, you have just to wait for the flag to be 1, which is the SSP IF. If the SSP IF is 1 for the transmitter, we have just to move the data from the counter to the SSP buffer. And for the receiver, for the slave, if the flag is 1, that means the data is ready. We have just to read it from the SSP buffer and send it to port. So if the SSP IF is 1, the transmission is complete. Okay, so we have to read the data. It must be cleared in software, and you have to read the data to clear the SSP IF. This is how to use the interrupts. Any question concerning the SPI module? So for the exam, you have just to focus on the concept of the SPI and the I2C. Okay.
So, in slide 30, can I have 2 master? One master to send the slave and another to send the another slave?
For the SPI, no. We have one master and multi-slave. For the I2C, yes. Okay.
Okay.
So it depends on the mode that you are using. In I2C, we can have one master, we can have multi-master. But generally, we use just one master because generally we have one microcontroller sending the data or receiving the data from, for example, sensors, or sending the data to screens or LCD. Or generally, we have one microcontroller. Okay. If you have 2 microcontrollers, in that case, we can have 2 masters, and this need arbitration. We'll see this in the I2C protocol. Now let's start the I2C protocol. So for the I2C protocol, you can see here that all the devices, they are connected in parallel. We have 2 lines. We have SCL and SDA. So SCL is for what? The CL. S is for serial. CL is for
communication.
So in serial communication, in synchronous mode, we need the data and we need the clock. So SEL will be the clock, and SDA will be the data. So you can see here that we have one line for the data, and we have one line for the clock, and all the devices, they are connected in parallel. So don't forget to add 2 pull-up resistors. So have to use 2 pull-up resistors to the DCC, okay? Without these 2 resistors, the communication doesn't work. So here, there is a problem. So let's suppose that device 1 is a master. How can the master select one of the slaves? Here we don't have chip select bit. How can we select one slave? Yalla, you are engineers. Give me solution. Let's suppose that this device is a master, and we have slave 1 and we have slave 2. How to select, for example, how to send the data to slave 2? So we have just one line for sending the data. Do you have any idea? Okay, so the idea is very simple. In this line, we have to send, first of all, the address, and then we have to send the data. So if the master has to select, has to send the data or receive the data from the slave 2, for example, it will send, first of all, the address of slave 2 to select the slave 2, and then it will send or receive the data. So here, what do we have? Simplex mode, duplex mode, full duplex, half duplex. What do you have as mode here? So for sending the data, we have just one line, and this line is bi-directional line. So which mode do we have? Simplex or duplex mode? Simplex means one device is sending to another device in one direction. But here we have 2 directions. So the master can send to the slave, and the slave can send to the master. So is it simplex or duplex mode?
Duplex.
Duplex. Now, it is half duplex or full duplex?
Full.
Full, what does it mean, full duplex? One line for sending and one line for receiving. Do you have 2 lines here for the data?
No.
No, we have just one line, which is SDA. So we have here one device sending to another device. So the 2 devices, they are sharing the same line for sending and receiver. So here we have the half duplex mode. Okay. So we can have the standard speed, which is 10 kilobit per second, and this is the standard mode, and you can have the fast mode, which is 400 kilobit per second, and you have the high speed mode, which is 3.4 megabit per second. Okay, so the data transfer will be serial, 8-bit, bidirectional. So the master can send to the slave, and the slave can send to the master. So here we have master-slave relationship with multi-master option. So here we can have multi-master as an answer to the previous question. Okay, so in I2C we can have multi-master. And if you have multi-master, we need arbitration. So which master can monitor the line? Okay. So the master can operate as transmitter or receiver. So the master can save the data or can send the data or receive the data. And we have seen that we will send the address and then we have to send the data. So the address can be 7-bit address or 10-bit address. You see now the terminology. So we have the transmitter. So the transmitter is the device that is sending the data to the bus. The receiver is the device that is receiving the data. So the transmitter can be the master or the slave. The receiver can be also the master or the slave. So the master is the device that initiates the transfer, and it will generate also the clock signal, and it will terminate the transfer. The slave that is the device that is addressed by the master. So the slave has just to wait to hear the lines and wait its address, wait for its address. If this slave is selected, then it can send or receive the data. So the multi-master mode is if we have more than one master, and we have this if we have, for example, 2 microcontrollers. So one of them will control the bus. That's why we need arbitration. So it is the arbitration. It is the procedure to ensure that only one master has the control of the bus at any instant. And the synchronization is the procedure to synchronize the clock of 2 or more devices. Let's see now the master and the slave. So the master device is the device that is in charge of the bus. So the master is responsible, is in charge of the bus. Okay. So it will generate the clock signal. It will generate the start condition and the stop condition. The slaves will just be listening to the bus, and they will act only if they are selected. Okay, so if the slave is selected, it can receive or send the data. So the master can send the data to the slave or receive the data from the slave. Okay, but the slave cannot send the data to another slave. Slave can send the data only to the master. It can send the data to the master. It can also receive the data from the master. We cannot have communication between slaves together. So the multi-master process, if you have more than one microcontroller, okay? So generally we have one microcontroller with another device. So it's rare that we use the multi-master. So if you have multi-master, we need to use arbitration, okay? So this is how to make the connection. So we need 2 pull-up resistor connected to the VCC. And you can see that all the devices are connected to these 2 lines. You have 2 lines, the SDA, which is the serial data, and you have the SCL, which is the serial clock. And all the devices, they are connected to these 2 lines. We have 2 wired bus. We have the SDA and the SCL. So the bit transfer is level triggered, 1 clock pulse per data bit. So at each clock, you can send 1 bit. It is stable during the clock, the high clock, and the data change during the low clock. So here we have the clock. Okay, so if the clock is 0, you can change the data. If the clock is high, the data is constant. Okay, it is stable. Now let's understand the protocol. Let's understand how does it work. So the transfer are byte oriented, and the MSB will be sent first. So first of all, the master will set the start condition. So it is a start condition. The SDA goes from high to low. This is the SDA, while the clock is high, and the clock is high. So this is called the start condition, and the master has to generate the start condition. Then the master will send the address of the state. So we can have 7-bit or 10-bit address. So here, let's suppose that we have 7-bit address. So the next 7-bit here will be for the address of the slave. And this master has to send the address. Then the master will send the read-write bit, because the master can read or write from the slave. So here we have to send the read-write bit. So if this bit is 1, that means the master is reading from the slave. If this bit is 0, that means the master is writing to the slave. And then the slave has to acknowledge by pulling the SDA low on the next clock. So here it is called acknowledgement. So the acknowledgement here is done by the slave. Once the slave acknowledges, that means the slave now is aware that is selected. Now we can initiate the transfer. So the transfer, according to this bit, it can be from the master to the slave or from the slave to the master. So this is an example of data. So this is the start condition. So the data goes low while the clock is high. Then the master has to save the address and the read-write bar. Then the slave has to make the acknowledgement. Then we have sending the data, then acknowledgement, sending the data, acknowledgement, sending the data, acknowledgement. And finally, if the master wants to close the connection, it has to generate the stop condition. So it is the stop condition. So the stop condition is that the data will go from low to high while the clock is high. So this is called the stop condition. So let's see an example, frame format. So if the master is writing to the slave. So the master. So if here we have shading, that means it is from the master to the slave. It is not shaded, it is from the slave to the master. Yani, so the start condition is generated by the master. Then the slave address is generated by the master. And then the read-write bit is generated by the master. Now let's suppose that this bit is 0. That means we have write. What does mean write? Yani, the master will write the data to the slave. So here the slave will make the acknowledgement, and then the master will send the data, the slave send acknowledgement. The master send the data, the slave send acknowledgement, etc. Once we have done, the master has to generate the stop condition. Now, if we are reading, and if this bit is 1, so the master has to generate the start condition. It has to generate the address of the slave and the read-write bit. So let's suppose that here we are reading the data. So this bit is 1. So the master is reading the data from the slave. What does it mean? Yani the slave will send the data and the master will send the acknowledgement. So first of all, we have an acknowledgement that the slave is ready. Then here the slave will send the data, the master send acknowledgement. The slave send the data, the master send acknowledgement, etc. So once the master done with the transfer, it can generate the stop condition. Is this clear?
Yes, doctor.
Okay, now I have a question. Let's suppose that we have microcontroller and you have 2 SPI or 2 I2C LCD. You have LCD 1 and LCD 2. And these LCDs are from the same manufacturer, with the same reference. So I have to connect these 2 LCDs to the microcontroller by using the I2C protocol. Now, if the master, which is the microcontroller, send the address of the LCD1 will be the same as the address of the LCD2. So how to solve this issue? Do you have any idea? Okay, so the idea is very simple. So we have 7 bits for the address. Okay, so 3 of these bits can be modified by the user. And these 4 bits are stable, unchanged. For example, if you read the datasheet of this LCD, you can see that the value here, for example, 1011. So this part is fixed address. We cannot change it. And here you have 3 bits that the user can modify. So if you put this bit to the ground, so here you have the value 0. If we put this bit, for example, to VCC, this bit will be 1. If we put this bit to the ground, the value will be 0. So if you have this configuration, the address will be 1011, and then you have 010. For the second LCD, we can select another address. So the first address will be the same, 1011, and then we have 3 bits. So with 3 bits, with these 3 bits, we can select any address, any other address. Let's make, for example, all the bits in the ground. So now the address will be 1011,000. So this is the address of the LCD2, and this is the address of the LCD1. So by using this technique, we can connect up to 7 or up to 8 LCDs from the same manufacturer with the same reference. Is this clear?
Yes.
Okay, I2C address. The initial clock has 7 address bit followed by the direction bit, which is the read write bit. Following clocks will have the 8 bit of data, and then we have the acknowledgement bit. The acknowledgement bit can be from the master to the slave or from the slave to the master. It depends on the direction of the transfer. So each address data byte is transmitted the MSB first. To allow the start and the stop condition bit generation by the master, the data line must not be changed while the clock is high. Okay, so it is only be changed when the clock is low. We have seen the start condition and the stop condition. Now for the acknowledgement bit, if the master is sending to the slave will send the acknowledgement. If the slave is sending the data to the master, then the master has to generate the acknowledgement. Okay, so the acknowledgement from the master to the slave. So in this case, the slave generates the acknowledgement signal because the master is sending to the slave. Okay, so the slave will generate the acknowledgement. When a not acknowledged is received by the bus, the master stops the transfer. The transfer has failed. So the master must generate the stop condition or repeated start to abort the sequence, and then the master can start sending the data again. Now, if the slave is sending the data to the master, in that case, the master has to generate the acknowledgement bit. So normally the master will generate the acknowledge after it has received the data. Okay. So if the master has done with the transmission, it can generate the stop condition. Okay, so we have seen this. 7 bits for the address and 1 bit for the direction, and then we have the bits of the data. And here you have the libraries for I2C. We have done with this chapter. Any question?
No.
Any question, شباب؟
دكتور بالنسبة